Good morning. Today I am going to explain digital modulation techniques. Yes, digital modulation techniques. Digital modulation techniques. Today I am going to explain digital modulation techniques. The digital modulation techniques are PSK, ASK, FSK, QPSK, and QAM. We are going to discuss this all different types of digital modulation techniques in our portion. Okay. Now, before going to explain this all, okay, first we have to know about M array modulation. In M array modulation, where capital M is equal to 2 power n, where capital M is equal to 2 power m, where capital M is number of levels, okay, and the small n is equal to number of bits transmitted in a single TB duration. M is a number of levels and n is a number of bits transmitted in a single TB duration. For example, okay, if I take n is equal to 1, by putting n is equal to 1, m is equal to 2 power 1 is equal to 2. So here the number of levels is 2. That is, bit 1 is a one level and bit 0 is another level. And so within 2b duration I can transmit either symbol 1, or within TB duration I can transmit either symbol 0. Right? So n is a number of bits transmitted in a single TB duration. So where capital M is a two levels, that is level 1 and level 0, or symbol 1 and symbol 0. So where n is within TB duration, we can transmit only one bit. Now another example, by putting n is equal to 2, m is equal to 2 square, that is equal to 4. So it means the number of levels will be 4. That levels are symbols, that is 0 0, that is a 2-bit combinations, 0 0 0 1 1 0 and 1 1. These are the 4 levels. Okay, these are the 4 levels. And here, because of n is equal to 2, so within TB duration either we can transmit this or this one. So within TB duration we can transmit 2 bits. Now by putting n is equal to 3, m is equal to 2 cube is equal to 8. So 3-bit combinations, that is 0 0 0 0 0 1 and so on 111. So these are the 8 levels we will get, and within each TB duration we can transmit 3 bits because of n is equal to 3. So it defines the M-ray modulation. Now today we are going to discuss PSK, phase shift keying modulation. So this PSK I am writing as BPSK, that is binary phase shift keying. Modulation and demodulation. binary phase shift keying, modulation and demodulation. Right. So before going to that one, what is the definition of BPSK? What is the definition? Right. So in every modulation, digital modulation, we required one is input signal, another one is a carrier signal. This is a carrier signal. This is input signal. For digital modulation, input is always zeros and ones. That is binary data. And carrier signal is a continuous time signal. Now, the definition of BPSK is the process in which the pace of the carrier is varied according to input data signal by keeping amplitude and frequency is constant. Once again I am repeating, it is a process in which the pace of the carrier signal, why it is called a pace, right? Binary phase shift keying. After I will explain binary. So phase shift keying definition is the pace of the carrier signal is varied according to input to data signal, where by keeping frequency and amplitude is constant. That is the definition, right? Now, why it is called B binary means here we are using m is equal to 2. That means n is equal to 1. Just now I explained, right? So here definition of this BPSK is the process in which pace of the carrier is varied according with input to data signal, where by keeping amplitude and frequency of the carrier signal is constant. Right? This is a definition of BPSK. Now, why it is called B binary? So just now in M ray signaling, I am putting m is equal to 2 means n value is equal to 1. M is equal to 2 levels, that is bit number 1 and bit number 0. And n is equal to 1 means at a single TB duration we can transmit either bit 1 or either bit 0. Okay. So that's why only 2 levels it is called as a binary phase shift keying. The block diagram of this one is BPSK. Okay, block diagram of BPSK. Input binary sequence, next one, it is passing through polar NRZ, and here we are using a balanced modulator or product modulator or a multiplier. Okay, this is called actually balanced modulator, and with high frequency carrier signal C of t with the help of local oscillator. C of t is equal to A cos 2 pi fct, and here I will get okay binary phase shift keying signal. Some books they are mentioning here band pass filter also. Okay. Now see here, let us take a binary sequence 10110. This is my binary sequence, and it is passing through polar NRZ, and output of polar NRZ we can call it as a B of t. Then that is multiplied with the high frequency carrier signal. I am getting here S of t is a modulated signal. S of t is a modulation signal. Now see here, for the input binary sequence, if bit 1 is transmitted, first let us call it as input sequence. Output of polar NRZ is B of t, carrier signal C of t, and output S of t. Please concentrate here. Now for example, first m is equal to 2, that is bit 1 or bit 0. So only 2 bits, only 2 levels. That is, for example, if bit 1 is transmitted, bit 1 is passing through polar NRZ. So we know that what is the function of polar NRZ, what is the level mapping of polar NRZ, where bit 1 is mapped to plus A volts and bit 0 is mapped to minus A volts. Already we are discussed. For example, let us take A is equal to 1 volt. So you will get here plus 1 and here you will get minus 1 volt. Yes or no? Now if input sequence, if bit 1 is given to polar NRZ, that B of t is mapped to plus 1 volt. And carrier signal, that is A cos 2 pi fct. And modulated signal is B of t is multiplied with A cos 2 pi fct. So plus 1 is multiplied with this one. So S of t is A cos 2 pi fct. Right? Next, if bit 0 is passed through polar NRZ, that is mapped to minus A volts, that is minus 1. Carrier signal is A cos 2 pi fct, and output is minus 1 into A cos 2 pi, that is minus A cos 2 pi fct. So here I am getting two modulated signals for bit. One is for bit 1, that is A cos 2 pi fct, another one is bit 0, that is minus A cos 2 pi fct. If you observe here, what is the definition here? The process in which the pace of the carrier is varied according with input data signal, right? Now see, whenever bit 1 is transmitted, here I want to write whenever bit 1 is transmitted, I am getting there is a no phase change in carrier signal. Yes or no? Whatever the carrier signal, that is A cos 2 pi, same A cos 2 pi signal I am getting here. Right? There is a no phase change in the carrier signal. So we can also be written as for bit 1 here A cos 2 pi fct plus 0 degrees. For bit 1 phase is 0 degrees. So you will get same thing. Now bit 0, see here, this is my carrier signal and modulated signal is minus A cos 2 pi fct. So when we will get minus A cos 2 pi fct, so due to 180 degrees phase shift of cos, you will get minus, right? So here A cos 2 pi fct plus pi. S cos 180 plus theta is equal to minus A cos theta. Right? Now see here, bit 1 is 0 degrees phase shift and bit 0 is 180 degrees phase shift. So here the definition is the carrier signal is varied according to, the carrier signal pace is varied according to input binary sequence. This is input binary sequence 1 and 0. When 1 is transmitted, my modulated signal is this one. When 0 is transmitted, it is 180 degrees phase shift signal, so that you will get minus a cos 2 pi fct. Okay. So this is a block diagram of BPSK. Now I am going to draw the waveform for this one. Right, 10110 we are. So input data sequence is input binary sequence. Binary sequence is 10110. This is input binary sequence. Now this is passing to polar NRZ. So polar NRZ, this is a time axis T, TB, 2 TB, 3 TB, 4 TB, 5 TB. This is a voltage level I referred. One is a plus 1 and minus 1 volt. Okay. We know that polar NRZ. Polar means here 1 will be, bit 1 is mapped to plus a volts, that is plus 1 volt. Bit 0 is mapped to minus 1 volt. Okay. So here input binary sequence 1 is, this is for, this is NRZ, non-return to 0. Within TB period it is not return to 0. So TB, and with 0 is mapped to minus 1 volt. Again here 2 ones, and this is my polar NRZ waveform. Polar NRZ waveform, right? Next, this is multiplied with what? High frequency carrier signal. Here carrier signal, carrier C of t, carrier signal C of t. Carrier signal amplitude is plus a minus a. Okay, here also. So here carrier signal. Just I am roughly drawing the carrier signal. Okay, this is my carrier signal. Now, and modulated signal S of t. Modulated signal S of t, the modulated signal when bit 1, please see here, when bit 1 output is a cos 2 pi fct, when bit 1 output is a cos 2 pi fct, when bit 0 output is minus a cos 2 pi fct, right? So here modulated signal S of t, that is BPSK, binary phase shift keying signal. This is T. Here what is amplitude? Amplitude of S of t signal is minus a plus a, yes or no? Depending on phase shift, a and minus a. So here this is, so before going to that, here I want to write first BPSK for bit TB, 2 TB, 3 TB, 4 TB and 5 TB. At TB duration, what is the BPSK output for bit 1? At TB దగ్గర ఏముంది? See here, this is a bit 1. So because of bit 1, output is a cos 2 pi fct. So here I am getting a modulated signal is a cos 2 pi fct. Here bit 0. From here to here bit 0. Bit 0 is minus a cos 2 pi fct. Again a cos 2 pi fct. Here again minus a cos 2 pi fct. So now see here, whenever bit 1 is transmitted, I am getting a cos 2 pi fct. Bit 0 is transmitted minus a cos 2 pi fct. Now here I am going to draw the waveform So up to this transition, the waveform will be constant. Okay. Now, whenever it is transition from 1 to 0, bit 1 to bit 0, here the amplitude of A is positive, and from positive to negative, here amplitude of A is minus A. Right? So what is the difference between plus A and minus A? How much phase shift? That is 180 degrees phase shift. So here you will get phase transition 180 degrees. So this is called time reversal. Again. Now again this point from TB to 2TB, it is transition is 0 to 1. So because of 0 to 1, this is a minus A and plus A. Again 180 degrees phase shift, that positive side. So ikkada emundi, A2 minus A is a negative phase shift, right? So that you will get negative transition, that is a negative time reversal. And minus A to plus A, positive time reversal, that is 180 degrees phase shift. Again, if you see here, from here to here there is a no phase shift, so signal will be continuously varied. Now again here 1 to 0 transition, so you will get negative. Again, okay, please see here, while you drawing this BPSK signal, whenever 1 to 0 transition it will be occur, the sign of A to minus A, yes or no? This is a plus A minus A. The phase shift is changing A to minus A, so that the time reversal will be occur at negative side, that is 180 degrees phase shift, and the transition is changing from 0 to 1, see here, that is minus A to plus A. So the present one is a plus A, so that the time reversal is occur, that is 180 degrees phase shift is occur at positive side with respect to time. Now see the definition. This is my carrier signal. This carrier signal phase, the carrier signal is phase is varied. How it is varied? According to input binary data or according to data signal, right? This is a definition of BPSK. The pace of this is the carrier, the pace of the carrier signal is varied according to input binary data signal. If you find here what is the amplitude is A, here what is the amplitude is minus A, the same amplitude of the BPSK. Amplitude is I am putting constant, and frequency of the signal is also same. There is no frequency changing in this one, right? So this is the modulation of BPSK. Okay, now next I am going to explain demodulation, detection of BPSK. Detection of BPSK. So the detection of BPSK, it consisting of two methods. One is coherent, another one is a non-coherent. One is a coherent and a non-coherent. What is the difference between coherent and non-coherent? So at the transmitter side we are using one carrier signal, yes or no? The same carrier signal, whatever the transmitter, so we have transmitter and receiver. So in the transmitter side we are using one carrier signal, and the receiver side also we have to use one carrier signal for demodulation. So whatever the pace you are used at the transmitter, the same pace will be used at the receiver. That is called as a coherent. So that the receiver is known what phase shift is changing in the transmitter, that same phase shift is also changing at the receiver. That is called as a coherent. Simple to say, that between transmitter and receiver the pace is synchronization. The synchronization phase shift is required in between transmitter and receiver, that is called coherent. Now I am going to explain coherent coherent BPSK. Binary phase shift keying, coherent binary phase shift keying we are going to learn, right? Now the block diagram of coherent BPSK is so this is at the receiver side, right? At the receiver side, what is the input? Input is the modulated signal S of t. So input is modulated signal S of t, that is BPSK signal, and it is given to a multiplier with high frequency carrier signal C of t. Okay, cos 2 pi fct plus cos 2 pi fct plus cos 2 pi fct. Then it is passing through a integrator. It is k minus 1 tb2 ktb into dt. The output of integrator, this is called integrator. Output of integrator, I am call it as S naught of t. And here I am using a device that is decision device. This decision device, it consisting of a internal voltage level, that is V threshold is equal to 0. Output is a demodulated signal. Demodulated BPSK. Okay. Demodulated BPSK. Now see here, just see this one here. Here, what is the carrier signal? Carrier signal is a cos 2 pi fct. This is our carrier signal, right? What is the power of carrier signal? Power means this is a AC signal. AC signal power is Vrms square by R. So the power of carrier signal, power is equal to A square by 2R. If put R is equal to 1, P is equal to A square by 2. So A is equal to, we can written as under root 2P, right? So some books they are writing here S of t equation. So see here our S of t equation is S of t is equal to a cos 2 pi fct for bit 1, 0, S of t is equal to minus a cos 2 pi fct. So some books they are written wherever the a they are writing under root 2p cos 2 pi fct, here minus 2p cos 2 pi fct. And also we can written as, see here, under root 2p cos 2 pi fct plus 0 degrees for bit 1, under root 2p cos 2 pi fct plus pi. So all the equations are correct. Please don't confuse. Okay. And also we can written as, see here, now when bit 1 output of polar energy is a B of t. Output of polar energy is a B of t. B of t, this is called B of t a cos 2 pi fct, and another one B of t a cos 2 pi fct. Some books they are also written as here, instead of that one, B of t into C of t. Here also B of t into C of t. Yes, all are correct. Now, now input is a BPSK signal, right? Input is a BPSK signal. So this S of t is multiplied with what? C of t. S of t is multiplied with C of t. Now S of t equation, S of t equation for bit 1, let us call it as for bit 1 anukundam. For bit 1, S of t is equal to SA cos 2 pi FCT plus 0 degrees, or or okay, or B of t into under root 2p cos 2 pi FCT. This is also correct. This is a B of t, NRZ output. Okay, this is a value and this is cos 2 pi FCT. Okay, now this is my S of t signal. This S of t signal again multiplied with a carrier signal. Again multiplied with a carrier signal. Okay, now see here, S of t equation is this one and carrier signal equation is this one. So here I am writing input of integrator. Input of integrator is B of t under root 2p cos square 2 pi FCT. This is input of the integrator. Here B of t's value is 1 or 0. Okay, depending on, just I am writing a equation which is common, not either not 1. This just I am just written here 1. Okay, equation 1, or here for equation 1 this value is plus 1. For equation 0 it is the value B of t's value is minus 1. Okay, I am writing here the overall equation, that is B of t, that may be minus 1 or plus 1, whatever it may be. Okay, now see here, just I explained here one example. Okay. Now this signal is passing through integrator, where integrator limits are k minus 1 TB to KTB. TB is a single TB duration, that is a kth TB duration. We are integrating 1 TB duration, that is k minus 1 to k. So 1 TB duration, right? So here this is input of the integrator. Output of the integrator is S naught of t is equal to integral k minus 1 TB to KTB, right? S naught of t. So wherever the t, just I want to written as this S naught of t because of KTB, kth TB duration. So I want to write one point here. Passing through integrator, where integrator is kth period integrator. Kth period integrator. So just I am putting wherever the t, just I am writing here KTB. So that is becomes kth period integrator. KTB. Here B of t. Here also t is there. So I want to write KTB under root 2p cos square 2 pi FCT into dt. Okay. Now see here, it is with respect to time domain dt. So B KTB is a constant term and root 2p also constant term. Now we know that cos square theta, what is the formula of cos square theta? Cos square theta is equal to 1 plus cos 2 theta by 2, right? So here I want to write k minus 1 tb, k minus 1 tb to ktb, k minus 1 tb to ktb 1 plus cos 2 pi two into 2 pi fct by 2. By 2 here I want to write. Done. Now into dt. B ktb, here it becomes p by 2. I want to separate the terms, k minus 1 tb ktb into 1 dt plus same b ktb the root p by 2 k minus 1 tb to ktb into cos 2 pi fct into dt. This is a Carrier signal and it is a periodic signal with one period. The periodic signal with one period integration is becomes 0. Okay. Now here I am getting b of ktb under root p by 2. By integrating with dt you will get only t. So by putting t is equal to ktb and t, here you will get t, the limits is k minus 1 tb to ktb. By substituting here you will get b ktb under root p by 2 and tb. So here I want to write this is S naught ktb. So the output of integrator is S naught ktb is proportional to b ktb, where tb and this entire time I am called it as a proportional constant. So output of the integrator is proportional to input data signal. What is a b of t? B of t is a S NRZ output. B of t is a NRZ output. So output of S naught ktb is proportional to S B of t. Clear? Now this output of this value S naught of t is passing through decision device. Okay. Now so output of the integrator we are giving to decision device, okay, where it compare output of the integrator with the internal level of threshold voltage. So decision device one input is S naught t, output is demodulated signal with internal level with th. This is a decision device. Okay. Now see here, this is output of the integrator. Output of the integrator is given to decision device, where decision device compare the output of the integrator with internal levels of threshold voltage, that is 0 voltage. Now see here, if S naught ktb is less than 0, S naught ktb, the output of this value is less than 0. So if the value is 0, right, what is a 0 value? This is a threshold voltage level. So input of S naught ktb is less than 0 means if it is a negative value, the decision device output receives, or output of the decision device it produces a favor of symbol 1. It produces a favor of symbol 0. Favor of symbol 0. If S0 KTB is greater than 0, it produces favor of symbol 1. See, what I am saying is, if this integrator output is less than 0 means if the integrator output is a negative value, if the integrator output is negative value, the decision device will produce the value bit 0. If the integrator output is greater than threshold voltage, this is a threshold voltage. So 0 is a threshold voltage. Greater than threshold voltage, that is positive voltage, it produces the output is bit 1. Yes or no? We are mapped here. When bit 1 is mapped to plus 1 volt and bit 0 is mapped to minus 1 volt. Right? If the integrator output is a negative voltage, it produces, decision device produces a value is 0. Okay. If the integrator output is greater than 0, that is a positive voltage, it produces the bit 1. So output of the demodulator we will get 0 and 1 depending on the integrator. Now I am going to draw the demodulation waveform. Here I am going to draw the demodulation waveform is of BPSK. Demodulation of BPSK, right? So that is with respect to time. So this is TB, 2 TB, 3 TB, 4 TB, 5 TB, right? See here, output. If the integrator value is negative, output is 0. If the integrator value is positive, output is 1. See here. So because of from up to this point, we are getting integrator value is positive. So I am getting a bit 1. Next, from here to here, what is the phase shift is? Minus A. Yes or no? Here I am getting minus A cos 2 pi f ct. So because of minus A, I am getting a negative value. So negative. Again, here there is a no phase shift. From here to here, phase shift is positive. So positive value from up to this point. And now this is demodulation waveform. So here I am getting 1, 0, 1, 1, 0. This is the same information whatever we are transmitted. The same information is received at the receiver. Right? This is the operation of BPSK. Modulation and demodulation. I hope all of you clear. Now I am going to find the bandwidth of BPSK. Bandwidth of BPSK. Now we are seeing for single TB duration, the value is 1, bit 1. Single TB duration, the value is bit 1. This is amplitude characteristic plus 1 volt time t. Now this one is shifted towards negative side. Here it becomes TB by 2 minus TB by 2, here plus 1 volt. Right? Now I am finding the Fourier transform for this one. The Fourier transform of that one is, we know that the formula of Fourier transform. Okay, the formula of Fourier transform is integral limits minus TB by 2 to TB by 2. Okay, what is the amplitude? Amplitude 1 into Fourier transform representation, that is E j2 pi ft into dt. Right? So is equal to. So here I am getting e power, this is becomes t, right? So e power minus j 2 pi ft minus tb by 2 by minus j 2 pi f, right? Now by substituting that, we will get e power minus j 2 pi f tb by 2 minus e power minus j 2 pi f minus tb by 2 by minus j 2 pi f. Now see here, minus and minus, minus becomes plus, okay, becomes plus. Now this minus I am going numerator side, so here I am getting e power j 2 pi f tb by 2 minus e power minus j 2 pi f tb by 2 by 2j pi f. We know that sin theta is equal to e power j theta minus e power minus j theta by 2j, right? I want to substitute this value here. So by putting this one is, it becomes sin theta. Theta value is equal to what? This entire one, 2 pi, and another one pi by 2. 2 will be cancelled. So here pi f tb by 2j. So now remaining is pi f. Now here I want to convert this one into sinc function. So what is the sinc formula? Sinc theta. Sinc theta is equal to sin pi theta by pi theta. This is sinc theta. Okay. Now I want to convert this one into sinc function. Here sin pi ftb. So this value and this value should be same, but here this value is not same as this one. So what I am doing, I want to multiply it with the tb numerator and denominator. So here tb sin pi f tb by pi f tb. Now it becomes the same. So it becomes now tb sinc, okay, tb sinc f tb sinc ftb. Now we know that the sinc function, how the sinc function will be represented. Now sinc function, amplitude is tb, right? This is a sinc signal. This value is as 1 by tb. This is frequency. Why? Because it is a Fourier transform representation. Here minus 1 by tb. So most of the power, it takes the most of the power in this only major lobe. So simply I am writing here, if single tb duration, the Fourier transform plus 1 is a sinc signal like this one. This is 1 by tb minus 1 by tb, frequency f. This is a input binary sequence. Next it is multiplied with what? Carrier signal a cos 2 pi fcc. The spectrum of carrier signal, we know that this is f. One will be at fc, another one will be at minus fc. The multiplication of these two the multiplication of these two is, I am getting a cos 2 pi fct. Multiplication of these two. The resultant multiplication of these two here, I am getting this is fc plus 1 by tb. Here fc minus 1 by tb. Similarly, at negative side, this is minus fc minus 1 by tb. Here minus fc plus 1 by tb. If you find the bandwidth of my BPSK is higher frequency term minus lower frequency term is, you will get the bandwidth is equal to 2 by TB. The bandwidth of BPSK is 2 by TB, right? Okay. Now, what is the bit rate? What is the formula of bit rate? Bit rate RB is equal to N Fs or N by Ts. Ts is a sampling time. Okay. So here the time period Ts and Tb is both are same, right? So N is equal to is what? N is equal to 1. In BPSK, N is equal to 1 and Ts is equal to Tb in this case. Okay. So that the bit rate RB is equal to 1 by Tb. Okay. Bit rate RB is equal to 1 by Tb. So bandwidth I am writing in the form of bit rate. Bandwidth is equal to 2 by Tb. This is also written as 2 into bit rate. Bandwidth of BPSK is equal to 2 into bit rate. Thank you. Now today assignment is once again I am giving the same assignment. The assignment is define BPSK. So don't write PSK. First you have to write what is B here, binary. Why it is called binary. Okay. After writing that one, you have to write definition of PSK. First you have to write why it is called BPSK. After that you have to write definition of PSK. Question, today question, that is 23rd 4 2012 assignment is define BPSK. First you have to write what is a B. Then you have to define what is a PSK. Right. Next one. What is a coherent? What is the meaning of coherent? And third question is calculate bandwidth of BPSK. Calculate bandwidth of BPSK and calculate bit rate. Bit rate BPSK and applications of BPSK. Okay, it takes 4 lines, it takes 2 lines. Okay, calculation will takes 10 lines or 12 lines. Bit rate it takes 2 lines. Okay, almost within 1.5 paper you will complete this assignment. Okay, everyone should complete this assignment and convert into PDF. You should send before 5 PM today. Thank you.